Good evening, my name is Clive Surman-Wells and I work for Northumbrian Water in the IS department as an applications team leader responsible for operational systems and GIS. I'm going to show you a few of our applications of GIS, real world problems, and show you how we've been able to work more efficiently and in some cases do things which we simply couldn't have done without GIS. Firstly though, a few words about Northumbrian Water. To set the context, we serve a population of 2.6 million people in the north for water and sewerage services in the northeast, and we also own Essex and Suffolk Water in the south, where we serve 1.7 million customers for water services alone. We've got 2,948 employees, getting 3,000. We maintain over 25,000 kilometres of water mains, north and south, and nearly 16,000 kilometres of sewers. This represents a huge logistical problem of managing those assets and ensuring that they are performing. We've been using GIS for well over 10 years now. We use a system called Star APIC, which is one of the lesser known GISs. It's used by accessed regularly by 800 users. That's 1 in 3 of all employees, and quite a few other employees will be indirectly accessing GIS data through other corporate systems where it's been fed through and made available. It's now integrated with, amongst other things, our work management and customer systems. GIS is Northumbrian Water's corporate repository for all underground assets, mains, sewers, and all the connecting nodes like manholes, valves, and meters. With over 300 data sets, which can be points of interest, areas of interest, lines of interest. I've highlighted some of those that we have. A combination of both external, where we purchased data off the shelf, the base mapping, OS master map, aerial photos, but other interesting layers of data, some areas, some point data, soil types for instance, and we've created an awful lot of our own data sets. Obviously all of our underground assets have been added by our own team of editors, and they can all be overlaid on a variety of scales of mapping. I want to elaborate on a few of the a few areas which illustrate efficiencies and improvements. Obviously there's not enough time to talk about very many of them, and I can't go into very much detail. And I'll finish off by talking about some of the slightly more obscure uses of GIS within Northumbrian Water, which nevertheless have been very useful to us. Well, operational planning and management, OPM is the first one I'm going to talk about. This is a system designed and written on top of our corporate GIS system in-house to manage and display the impact of planned and unplanned water supply events to aid incident management. So that's things like loss of water supply or discoloration of water. It lets you know when an event is occurring as the event unfolds, and provides tools for managing those events. It also allows you to plan events as well and see the impact and do some what-ifs. If we turn this valve, what happened? Who will be affected? If we wanted to do some mains flushing, for instance, who do we need to tell? Who do we need to drop leaflets to? And of course, when something goes wrong, which affects customers' water supply, Northumbrian Water have to respond rapidly and decisively to ensure a continued water supply. We have linked customer calls received by our call centre, which are contacts, known as contacts, to GIS, and developed an early warning system. So that first screenshot there just shows you more than you can get from a few phone calls. It's telling us where the phone calls are coming in from. So how do you decide as early as possible that a single call received by one of 100 call centre staff is part of a larger unfolding problem? We need to decide quickly whether or not it is an isolated event or whether it's part of something which may be affecting others. In this screenshot we've represented the no water telephone calls. That's real data, so from an area in West Rainton. Initially the dots don't actually appear in front of people, but we've plotted them in that way. But behind the scenes network administrators can set up a series of alerts that will send them an SMS or an email, which I'll show you in a second, that tells them a threshold has been exceeded and there could be something going on, and that will direct them to creating an incident. In the second screenshot on the right there, what we've overlaid on there is a district metered area, which is kind of the DMA of the water network. All of those properties within that boundary will be supplied by the same piece of water network. So it's obvious there's something going wrong in that particular DMA, which will really help our network analysts. So I said our analysts can define rules which will fire alerts. For example, there's an email there that's a real one, which is let us know if there are any, if we receive more than 3 instances within 60 minutes of no water contacts, that's telephones in the call centre, within any particular supply zone. And they'll have zones that they're particularly interested in, and the thresholds will be different. The analysts can set their own thresholds. Once the analyst defines the event, so in that last example they say, right, okay, there is something going on, I'm going to define an event, we're going to call it Rainton and give it a date. That becomes visible to the people in the call centre as an event. So as phone calls are coming in, they can see on their screen there is something going on in that area, and they can reassure the customer, we know about it, we've got network analysts going on, there is a problem with pressure or discoloration or no water. The OPM tool goes a bit further than that, though. It splits the affected area into 200 metre squares and calculates the centroid of the properties affected in each square to calculate the best place to set up an alternative water supply, such as a static tank. So those plots get given to the guys on the ground who go out and place static water tanks. That information is available to the people in the call centre, so as calls are being received, the customer can be directed to their nearest water supply, given information. Of course, the bowser or tank might not actually end up there, that's where it's been calculated. The guys on the floor, out in the field, who actually site it can come back and later and move the position of the dot so the call centre can see it if it's not convenient, for instance, to put it there. So OPM provides many other efficiencies, such as listing in a hurry, which is useful in this sort of events, lists of customers with special needs, people like kidney dialysis patients, schools, hospitals, where we want to get bottled water out to them as quickly as possible if necessary. And we can also produce lists of properties affected, which can be used to distribute leaflets. We can give lists of streets and addresses to guys in the field who can drop those through doors. So that's the OPM tool. Now, failure frequency analysis of mains, several ways of doing this, depending on whether you've got information about actual bursts, which we do on our distribution mains, but on our strategic mains, we don't really get very many problems on those. So what you have to do if you're analysing where you are trying to predict a failure of a strategic main, you've got to use the information we have, and we use what's known as a tendency tree. So we look at operational and physical factors, we look at our strategic mains and calculate the risk of failure based on the material of the pipe, the diameter, the age and the joint type. All of those attributes are held against every pipe on the network in GIS. That's data that's associated with the attribute information. However, things get complicated though when you introduce factors such as soil characteristics, soil corrosivity, and where the main is laid in relation to other things, the verge under the pavement, under the road, next to a river, for instance. All those things will have a factor on how frequently the main is likely to fail. So, overlaying the two pieces of information, that's the soil information there on the right. You can see, I don't know if you can read it, actually says soil description, and it's got a corrosivity factor of the soil. We'll combine those things, but we won't do it graphically. What will happen is we'll have an algorithm behind the scenes which splits the mains up. As they cross soil boundaries, it will calculate a risk factor for each section of pipe, so different sections will have a different risk associated with them. Nevertheless, it's quite interesting to look at when they are overlaid, but that's not how we actually do it. We're still using the data that's in GIS, and we're using GIS functionality for software. Building height data and threshold data is another thing we hold in our GIS. We've got a data set for buildings over 12 metres tall, and this was requested, interestingly, by our pressure and leakage team. When the network analysts are managing problems related to pressure, then those customers who live on higher ground or in tall buildings are going to be affected first. We've colour-coded that for the guys who are managing that. The plot on the right is simply threshold height, based on the building, giving you a heads up on who's going to be affected first. This is the TMA coordination schedule. Not a great deal to see, but one of the problems we have sometimes is in a large organisation you've got teams of people working in the field, and they're working on completely different networks, the sewerage and the water side. They don't necessarily know where the others are going to be working or where they're planning on working. So the TMA coordination schedule is used to allow one department to publish to the others where they're planning on working. So you can see there's no nasty surprises on site when two people turn up on the same site. We'll use that as well in conjunction with